Howdy, Spanish campers. It's me, the Rob, doing a rather impromptu stream, and I'm actually going to check to see whether or not this is actually on my channel. It looks like it's on my channel. Let me bring this up to mute that. All right. Looks good so far. I'm going to. Should I keep that open? No, I'm going to kill that. All right. So, for those of you who come across this, you might be wondering, Rob, it's 1:30, 1:22 in the morning where you are. You just bored and like, why are you streaming? Well, the reason for this is I'm doing a project that I've had in the back burner for years. I collected this data back when I was a lab instructor at Emory University. This data is photometry on a binary star called HL Auriga. And it's really just been kind of a thorn in my side in that it's one of these things where I've gotten the data and just I've tried to reduce it, I've tried to analyze it, and then something happens and I don't. So I thought couple things. I thought, all right, well, one, I want to do it again. I've got more resources now, more experience under my belt. Let me try to analyze the data again and see where I can go with it. And I figured I might as well stream it for a few different reasons. One, it will hopefully give me more of an impetus to actually get it done. If I'm held accountable in some weird existential sort of way. But I also think it's instructive in that I've entitled this stream "How the Sausage is Made," and so what I'm going to do, and I will freely admit that a lot of this is going to be fairly tedious. May not be the best entertainment or best TV on out there on the YouTubes, but considering that Blue Marble Science can get away with showing a red laser dot moving slowly, going back and forth over a span of hours, and people don't seem to complain, then, I don't think people have room to... I think maybe there's an audience out there for this. What this is intended to do is to illustrate how science is actually done from an astronomer's point of view. And so this is very rudimentary work, what I'm going to be doing. What I'm doing is I am doing what's called time analysis or photometric time analysis, meaning I am looking at the brightness of a astronomical object, in this case, an eclipsing binary star, and I'm looking at how the change of the brightness of that object, as it appears to us, how that change in brightness, how does that brightness change? Does it change with any periodicity? What is the amplitude of the brightness change? Meaning, how bright does it get? How dim does it get? So forth and so on. And I may have already said this, is there any periodicity? Essentially, if I can characterize the variability of this star, if I can characterize in time, not only in time, but also in shape and amplitude, how the star is changing its brightness, I can then go to a more interesting question of why is it doing it? Obviously, part of the reason is the fact that it's an eclipsing binary, meaning that you have two stars. Actually, hold on. I knew this would come in handy at some point. Apologize for the lighting, but I like mood lighting. So you have these two stars here. Ignore the black bar. Say you have these two stars that are sitting out into space. Well, these two are going to be orbiting around a common center of mass, which is where my hand is. And as you can see, roughly speaking, they're going to orbit around. Well, if the orientation of this orbit is fortuitous, then what you'll see is that one star will pass between you and the other star. So this star is now blocking all of the light from this star. And so when it's say in this orientation, you can see the light from this star and this star, here, one of the stars is being blocked out, and so all of that light goes away. And so the star system is going to appear dimmer overall. And then as it continues to go around, the brightness is going to be fairly constant, although not necessarily completely constant, and I will hopefully explain that later on. And then the reverse will happen. The other star will now move in front of the other one, blocking out the light from this other star, causing the light to decrease yet again. And then as the star system continues, the light's going to return to some nominal level, and then that's going to repeat with some periodicity. That's an eclipsing binary in a nutshell. HL Auriga is a very specific type of eclipsing binary called a W-UMA. Now, W-UMA is a fascinating type system because it is a binary system where the two stars, this would be considered a detached system. These two stars are far enough away from each other that the mutual gravity between them isn't really going to affect their overall shapes. They're going to basically still be spheres just orbiting around a common center in space. But if these two stars either formed very close to each other or for whatever reason got knocked into a much closer orbit, then instead of two well-established stars that are both spherical under their own gravities, the mutual gravity between them will cause them to distort and actually become more peanutty shaped, to the point that if they're close enough, those peanutty shapes, or those little points, will touch, and the star will actually have a common envelope. While there are two stellar cores, it'll have one stellar atmosphere. And so you have two stars, but one atmosphere. And this thing is moving around very, very quickly. You're talking about two stars orbiting around a common center. I believe HL Auriga, it's been a while since I've returned to this, but I believe HL Auriga has a orbital period of around 3 days. Not quite 3 days, but around 3 days, meaning it revolves once around itself every 3 days. Now, you can imagine the speeds at which it's going around, but it's going around tremendously quickly with a common conval envelope. And one of the consequences of this geometry, of the physical nature of this, is that it causes the magnetic fields to become highly intense, to be very, very intense. And if you have large magnetic fields on a star, you inevitably have star spots. You'll have patches of the star that are colder than the surrounding environment. And so this magnetic field gets all wonky, and it will cause parts of the star to actually cool off, and you'll have these dark spots on it. So imagine if this is a really bad example, but I'm running out of toys. Oh, imagine kind of like the opposite of this. Imagine that the ball here, the 8-ball, is actually white, and this white spot is actually dark. So it's kind of the inverse. So this would be a star spot on the surface of a star, and as the star goes around, that spot will cause the light. Hopefully, you can see that the presence of this darker spot, meaning that there is less light coming out from this localized region somewhere. This localized region will cause the overall light to change. Here, you're not getting as much light as if the spot were on the other side of the star, and now you're seeing the entirety of the surface of the star at the same temperature, and so you get more light. And then that spot comes in, blocks out some of that light again, and so the star's brightness will change due to spots, as well as due to the fact that it's a binary where one star is blocking out the light of the other. So it's a very complicated system. But what I'm doing, the analysis that I'm doing, is pretty rudimentary. As astronomical endeavors go, this is actually pretty straightforward stuff, at least in the very beginning. And so I thought I'd just, share it with whoever wanted to see it. And just kind of document, kind of have a research diary to just document what I've been doing. So, all right. It is kind of weird. I am jumping not in the middle of the project, but in the middle beginning. So there are a few things that I haven't touched on yet. And I don't know whether or not I want to spend the time to do that. Let me do this. I'm going to pull this over here. That's not what I wanted to do at all. Oh well. Let's take. Nope. Yep. All right. Let's stick you over there. Let's bring all the windows that I might need over here, and all the windows you guys don't really care about over there. So I'm just switch things up a bit. All right, that's good enough for government work. All right, so what do we got here? Let me look at myself. All right. So what do we have here? So what I'm doing here, what we have on this screen, the busyness that is going on, is so I'm using a program called Astro Image J, or AIJ for short. It is a free program. Anyone can download it. It's very simple to install, and you can install it on any system. There is a Windows version, there's a Linux version, and there's a Mac version. I've used all three. This is currently the Windows version of AIJ. I have the Mac version installed on ye old Mac. And I have an old Linux box at home where it's installed there. I will say that it runs great on all systems, although the Mac, when Mac updates its systems, AIJ decides more often than not AIJ is going to feel the brunt of that. So if you want to use AIJ, be careful of updates, is all I'm saying. Now, AIJ is a phenomenally powerful tool, particularly given the fact that it's free, that somebody decided to put all this work creating the software and put it out there for everyone to use. It's just, if I knew who they were, I would shake their hand. They're awesome. So the way that and I hope to make content later on that elucidates these points a little better. Talks about what a CCD image actually is, what the calibration frames are, so forth and so on. But for now, what I'm going to basically just say is, and I'm going to sweep those off. This is an image a CCD image, basically a digital image I took of the HL Auriga binary system and its environment. HL Auriga is this one right there, is that system. Now, I say it's a binary star because there are actually two stars in that location in space. We only see one because of the fact that it is so far away and the stars are so small. Our ability, even this was taken using a 24-inch telescope, or a 0.6 meter, if I can do units right, basically a 0.6 meter. The 0.6 meter did not have the resolution, or does not have the resolution, in order to resolve those two stars as individual points. I can only see them as a single source. The light is emanating from those two stars, but I do not have the resolution in order to distinguish those two stars as separate individuals or separate entities. So all I can do to determine that there is, in fact, a binary system there is to look at that system over time and see how the light develops, see if it changes in any way. And the way I do that is via a way called differential photometry. So I'm not going to get into the nitty gritty of magnitudes and all that kind of good stuff here. In another video, I will talk about the lovely Hipparchus and how he has saddled us with a somewhat counterintuitive system, although I guess it could have been worse. What I'm going to be talking about primarily here is relative flux, basically, or relative brightness. And so what AIJ does is it's going to compare the brightness of this star with respect to companion stars. So the companions that I've chosen are this one, this one, this one, and that one. They all have very romantic names, like this is HD 43456. This one is TYC, or the star from a Tycho catalog, which is TYC 3383456-1. You get the point. Really beautiful names that are very memorable, fly off the tongue. Needless to say, these are stars that are relatively the same brightness and reasonably the same color as my target. Now, they're not exact by any stretch. We would like them to be exact because it would just make the analysis easier if it were. And hopefully that will become clear. Definitely not tonight, but maybe later on as we get more into this project. But if your companion stars, if the stars that you're comparing are close to the same characteristics as the star that you're analyzing, then the systematic errors that get included are less than if you're looking at if your target is a really red star, or if your companion is a really blue star. So comparing a really red star to a really blue star, you can do it. It's just going to add a little bit more error to your back end. What you really want to do is you really want to be able to compare apples to apples as opposed to apples to literal oranges. Or literal giant blueberries, for example. But because we are kind of stuck with what the universe gave us, and so with this field of view, basically this window that we are able to take a snapshot of the universe, we have really only a small number of stars that are bright enough to give us good enough quality data for us to do any sort of comparisons at all. So like I said, those are these stars, and I will point to those directly later on. Now, I have data spanning 5 different nights. They are those nights, if I remember correctly. Let's go here. This data was taken, the first night is January 23rd, 2003. The second night's worth of data was the January 24th of 2003. The third night is the 27th of 2003, and then the 28th, and then the 3rd of February. So these were all taken within 5 nights over the span of about a week or so. Like I said, the orbital period is around 3 days. So the strategy behind doing this. So with physicists, when you're trying to prove something in the lab, if you're trying to, test, do the science of cutting, which is an inside joke, which none of you will get. But say you wanted to know what the resistivity of a particular element is, like how resistant is a particular element to passing electric current through it. You'd basically develop an experiment within a lab, and you'd set things up, and you'd be able to control the various variables involved, and you'd be able to directly measure that resistivity, whatever it happens to be. In astronomy, it's not so clear-cut. Obviously, we don't have a lab that we can stick these stars in. I can't just take this star system, stick it in in a basement somewhere and just watch it over time from across the table. So what astronomers have to do is when they devise an experiment, what they really need to do is they need to devise an observation strategy. Part of that strategy, particularly in terms of what I'm doing, is you need to know for how long overall you need to observe this object in order to get the data that you need. And you need to know, which I refer to as the temporal baseline, how much data do you need from start point A to point B? You need a week's worth of data? Do you need a month's worth of data? So forth and so on. The other thing you need to know is how often do you need to look at this object? How quickly does this object change? If you're talking about something that is variable on the order of months, then you probably only need to look at it every couple, 3 days or so, because looking at it every day, the difference in the variability is probably going to be very minor. So you're really not getting much in terms of, I mean, if you've got the time, if the telescope is available, sure, why not? But chances are that's not going to be the case. So you need to balance out what is feasible with what is practical or what is necessary. So if you are applying for time on a telescope somewhere and your object only varies once every month or so, checking in on it every, say, 3 or 4 days would probably get you enough science data in order to prove, to tease out what that variability is. You certainly don't need to look at it every day, and you certainly don't need to look at it like I did with HL Auriga, which was I looked at it constantly from when it rose to when it set, because, as I said, the rotation period is on the order of 3 days. And I want to be able to get as much data as I could quickly. What I want is what we call data over 3 rotations or orbital periods. So I want to have data such that I've seen this thing orbit 3 times going around. 3 times going around. And so and because the variability is so short, essentially I need to sit on it for as quickly as I can, or for as much as I can, because the variability changes, as you can already see on the graph, fairly significantly over the course of one night. So that's my observational strategy. So in brief, my observational strategy was to look at a system like this, which is a very fast orbital period. I want to look at it over enough rotations that I have a large enough data sample so that anything that I see is statistically significant. Generally, 3 is a good rule of thumb. So if something is variable, looking over, getting data over 3 different variations is statistically significant. Because if there's going to be any changes between one rotation or one rotational variability to the next, or I should say one cycle of variability to the next, you can see that, or at least hope to have some kind of indication of that over 3 cycles at the very least. So you want to have at least 3. That's kind of the rule of thumb. And like I said, because of the fact that this system changes its brightness fairly quickly, my observational cadence was essentially as fast as I could take data. I was blessed in that this project was the test run, as it were, for the Emory Observatory at Emory University. So this was the first time the data was actually being taken with it. So this was basically its shakedown cruise, as it were. So I was blessed in that I had as much time on this telescope as I wanted. There was no other programs to compete with it. So I took all of this and took all of that data, and that's basically, long story short, that's the observational strategy is take data very quickly over the entire night, over at least three variability cycles. And I can do that over the course of 1 week because of the shortness of the cycle and the fact that, again, I wasn't competing with anybody. The only thing I was competing with was weather. And we'll see later on a good chunk of my data, or a reasonable chunk of my data, I'm going to have to cull or get rid of because of the fact that clouds came in. It just wasn't optimal for taking observations. And also, I missed nights because there were gaps in the nights because the sky was cloudy at that point. So I could not actually take data when I wanted to. So if it were up to me, I would have taken data every night over, say, 6 nights. But it got cloudy. Stupid atmosphere. Yay, I have a fridge. So now I have soda on demand. Woo! In a sec, I think I'm going to make some coffee. All right, so where do we go from here? So that's the experiment. That's the experiment of an observational astronomer. Figuring out what kind of observational strategy is going to give you the best data for the cheapest amount of time. Because telescopes, research-grade telescopes, are what we call overly subscribed, meaning that there are too many projects for the number of telescopes that we have. For those who like to complain about how much money NASA gets, it ain't nothing. In comparison to what we need, what astronomers need, and I don't know, I'm using the word need kind of, obviously there are hierarchy of needs, but in order for us to achieve all of the goals that astronomers have set for themselves, the NASA's budget is pretty, it could be higher. Give us more money. Anyway, so telescopes are typically oversubscribed, meaning that there are far more projects that people want done than there is literally time in the night, given the instruments that we have. So as an astronomer, you have to balance those issues. You have to create a strategy that is as impactful for the least amount of time. And that will appeal to the tax. That will appeal to those telescope allocation committees, those powers that be that decide, yes, your project is cool, we shall give you some time, or no, your project sucks, come back when you don't suck anymore. And yes, that's exactly how that runs. So that's basically how this got set up. So I have a load of data, lots of probably close to 500 or so images or so. Forgetting one major thing. So I was thinking that I only had maybe 500 images or so to deal with. That's not really accurate. I have about 500 images in a particular filter. So as you can notice from the image that you can see on the screen, this image is black and white because astronomers, we are interested in that is on purpose. The image that you see there is only allows a certain range of visible light to go through, specifically the very, very red part of the IR spectrum, or part of the visible spectrum. This is in what we call the I filter. And the reason for that is because of there is a physical reason or physical motivation for why we do this. If we look at the light in only small chunks of the visible spectrum, that allows us to analyze In this case, temperature. In astronomy, it's a little bit reverse. It's a little bit counterintuitive. The hotter an object is, the bluer it is. So unless you're a welder, you probably are more akin to blue things being colder than red things. But in astronomy, the bluer something is, the hotter it is. So if you can look at the light coming from an object in the blue part of the spectrum, and you sum up all that light, and you compare how much light you're getting in the blue part of the spectrum to the amount of light you're getting in the red part of the spectrum, that is a proxy for temperature. If you get more blue light than you get red light, that's a blue object. It's a hot object. If you get more red light than blue light, then that's a red object. That's a colder object. Not cold by any stretch of the imagination, but colder. And if they're about equal, then you have something that's kind of in the middling, like the sun. So I have taken data, roughly the same amount of data, over 5 different filters. So I have looked at the really, really blue part of the visible spectrum, or U band, the blue part of the spectrum, or B band, B as in boy band, the green part of the spectrum, or visible for some reason, the red part of the spectrum, or R, and the really, really red part of the spectrum, or I. And so I have roughly 500 images in each of those filters over the 5 nights. So overall, if I can do math real quick, what is that? Something like 2,500 images I need to analyze. So that's one of the reasons why I have not actually completed this project, because that's a lot of data, which I'm not complaining, just, it's a lot of data. So what I've done here is, because it is so old, because this data is old, roughly at this point, it's nearly, oh good God, it's nearly 2 decades old. I'm so old. Anyway, the notes that I took, if I took notes back then, I don't have them anymore. So there's a lot of, there's going to be a lot of, why did I do it this way? Okay. Moments during this project, and so I have to essentially approach this as if I have no idea, or have very little idea, of how these observations were actually done. This is kind of a no-no. So if you're watching this and you are thinking about doing astronomy in any kind of research or professional way, what I've done here is kind of a do not do lesson, or a kind of what's what I'm looking for. There's a phrase, and I'm not imagining it right at the moment. Yeah, well, all right. Anyway, cautionary tale. That's the right. What you want, even in this day and age, you want notes. You want to write down what happened. Pretty much, if you may not need to write down if you sneezed, but if there was a hiccup, if your observations crashed for whatever reason, you write down time. It crashed here, came back up here. What filters did it affect? Basically, write down as much information as you possibly can when you take the observations, because that will make your data analysis way easier on the back end. Because I don't have these notes, because I don't know when clouds came in at certain times, I'm going to have to go through each of these 2,500 images and basically make sure that the data is consistent and can be interpreted by the AstroImage-J program appropriately. And that'll make a little bit more sense as we move forward. But yes, take notes. Pro tip: always take notes when you were taking data. Even if it seems tedious, even if you don't want to, you never know what you might need later on. So spare yourself the later on heartache, and just write it down. Simple things. So what I've done here is I've taken the data from the I band, as I said, and one of the things that we noticed, this is the whole thing run through. All right, right over here, this plot right here. HL Riga are these blue points, and these little error bar or these little bars that go up and down are what we refer to as error bars. That means that for this particular, for example, for this particular data, the relative flux relative to the other stars in that image that I tested, the target star, HL Riga, is actually around 17% brighter than the ensemble brightness of all of the other comparison stars. But there are errors. There are systematic errors in the data collection that cannot be ignored. So it is not a definitive number. It is not something I can say, yep, it's 17% exactly. No, what I can say is that it's roughly 17%, plus or minus 1%. That looks to be. I'm getting about 1% errors on that particular data point, and they change. Depending on the overall quality of each particular image, because each of these data points corresponds to one different picture based on what the error or what the noise, background noise is in that image, what it's doing in that on that particular image is going to affect what these systematic errors are, what this error bar is going to be. So if the background is really noisy, like for instance, if clouds came in and the background was really choppy and some pixels were brighter than others because there was a cloud in the way or what have you, then that error bar is going to get much larger or appreciably larger. If it's clear skies, if it's perfectly flat, if there's nothing out there at all, then the error bars are going to get smaller. Other things that affect it are like, what was I going to say? Temperature, the CCD temperature. How hot is the sensor? The colder, the better. Other things that affect it are whether or not I have properly characterized the camera for the software. I'm not going to get into the weeds on that, but essentially, I am making guesses as to certain technical certain technical details about the camera. The fact that they are estimates adds to that error, but not appreciably, not to the point that you can't take this data on face value. But those are the kinds of things that get thrown into making this particular error bar. And as you can see, over the course of the night of the 23rd of January 2003, we have as the HL Riga started off on some nominal level, and then it did this little dip thing. Who knows? It popped back up, and then it came down, and then it eclipsed. So one star passed in front of the other one. It popped back up. That star passed. So one star moved in front of the other one, and then moved out of the way. And then we could see the two stars as one moved away. You could see the light from the two stars coming in back into view. If we had more than say 12 hours to look at this object, if we could look at this object for basically during the day, what you would see is that this cycle would repeat itself. So this would be the primary dip. So these two stars would be like this, would give you this primary dip. This would move out of the way. The brightness would increase until it's like this. That's where you get this happy maximum up here. And then it would come around and like this again. And you can imagine it's going to be over here. And then as this star passes in front, it's going to cause the brightness to drop again and so forth. As we get more and more data, that's going to become more obvious, the double dipping essentially. The continuous change in the brightness of the binary is going to become more obvious. So, okay. So yeah, the blue points indicate that the star's brightness is obviously changing with an amplitude of roughly 50%. So this star is changing with an amplitude of about 50%. It's losing that much. These points, the red, the fuchsia, and the purple, or the dark red, the light red, and the fuchsia, however you want to look at it, these are those companion stars. These are the stars that I, a priori, do not expect to vary. I don't think that these stars are variable. And that's actually a key point that I should probably back up and make. When you are designing your experiment, when you're designing your observations, what we're wanting to do is we want to compare the brightness of HL Riga, or your variable star, to a constant source. Because or constant companion, if your companion varies, then you won't be able to tell when you look at the final output, when you see that the light is varying, you're not going to be able to tell whether or not the light is varying because of the source or because of the companion. The only way you can tell that is if you assume or can figure out via some by some clever means, that the companion is in fact normal. If the companion is in fact constant in brightness. That is one of the reasons why you take comparison data from multiple stars. Because what I can do is first off, I can see whether or not the brightness changes of, say, this purple one or this fuchsia one, if those brightness changes correlate, if, for example, here, this little structure, this little upward motion of HL Riga kind of corresponds to here. So it leads me to believe that maybe if I were just looking at this, it may be that the light was increasing here because there is something going on with the companion star. So, for example, and it might still be, because it might be that this hump that I see here, this structure that I'm highlighting, I'm hoping I'm highlighting, that may in fact not be real, because it may be light coming from the companion star. That's something that I'm going to have to investigate. Because if I can see any correlation between, as the companion goes up, the target goes up, then I cannot just assume that the change in brightness is because of the target, of anything that's happening in the target. It could be because of something that's happening on the companion. And when I look at the other stars, I'm starting to wonder whether or not this fuchsia one there may be something funky going on here, because these are all correlating with themselves. The light red and the red seem to be agreeing with themselves on how the light should behave, and the way the light is behaving is more indicative of the overall conditions in the sky, than it is for any particular star. And you can also notice that this motion, or this dips, or these changes in brightness, do not correlate really well with this data here. And so that's later on. Essentially, that is going to be when I'm looking at this data more closely. Right now, I just want to get the relative fluxes, just want to get the relative brightnesses. But once I have them, then I need to take a closer look at that data to see whether or not some of it may be erroneous because of the strategy that I employed in order to get this data. This is essentially the way that astronomers are able to control the variables, control particular variables that are obviously not within their scope of, you can't, like I said, you can't physically manipulate these things. So you have to develop tricks to be able to suppress any kind of variability that may stem from a variable you're not taking into account, or taking into factor, as it were. And yes, I am just going to drink straight from the bottle. All right. Woohoo! All right. Well then. So, yeah, just looking at this data, there's a lot of structure here that I would not expect. Like, I don't know why. I would expect a fairly continuous change in brightness as the star moves, as the star revolves around. If there are spots on either one of the stars, what I would expect is sort of deformations or slow changes in the brightness. So, for example, when I'm looking at here, I see that if I look at the slope on this side, if I look at the slope on this side and I look at the slope on that side, basically how quickly does this thing dim over time to how quickly this thing brightens over time, I notice they're not the same rate. And so what that tells me is that there might be a spot over on this side, which is causing this thing not to brighten as quickly as it would if the spot weren't there. I don't know. That's going to be for way in the future to figure out. And then, of course, you've got, again, it gets a little bit muddy, it gets a little bit wonky. Not sure if any of this is real or physical, but we will see with more data and more analysis. But overall, I'm happy with my companions. They don't vary more than, say, 10% in brightness. It's not great, but I'm hoping with more data I can stamp that down. And there are techniques I can use to essentially cull data that I do not have any faith in, based on the quality of the rest of the data in the sample. And so hopefully we can knock that down. But overall, it definitely shows variability. It seems to indicate that there is evidences of spots, but this is way in the future. This is all very, very preliminary. So what I'm going to do now is I have blocked out block one. I have blocked out the ith filter, and I am now going to move on to the rth filter. The R filter. Where is my cursor? There it is. And so one of the things, let me back this up. One of the things is that AIJ does not take well to trying to analyze data that jumps, if the images jump around a lot. And so I need to basically split this data into digestible chunks for AIJ to operate with. As you can see here, some of the data has already been culled. Basically, some of this may have been there was some problem with the telescope. Again, I don't have notes, so I don't know. But some of this data was omitted, and some of it I omitted myself because clouds had rolled in, and it was obvious that the data that I was going to get was going to be crap. So I just didn't analyze it at all. That's why there's a gap in the data there, and it's also probably why there's a gap in the data there. So now I need to get the R filter data all squared away. So, again, speaking more pro tip here than anything else, I'm going to be doing a lot of the heavy lifting analysis using Python later on. But for the preliminary kind of stuff, I cannot oversell Excel. Excel is a wonderful, wonderful tool, particularly when you're dealing with hundreds, if not thousands, of data points. It is a wonderful tool for collecting that data, amassing that data, and doing simple to even fairly complex analyses on that data. A good chunk of my thesis was using a a spreadsheet, which was like 13, 15 meg in size. So it was, for a spreadsheet, it was ginormous. Anyway, so just a little pro tip. Excel, Zang. All right. This is where the boring parts come in. Let me bring this over here so I don't have to look away so often. I don't think anyone's watching this live, but if you are watching or not watching this live, you can probably skip ahead for the next 20 minutes. What the fuck? This also will help with my time management, because now I know exactly how long I've been working on this. So I am not Team Skeptic. I will not be going at this for 6, 8, and 10 hours. I will be going at this for 3, 3.5 if it gets spicy. $13 blocks. One of the things that I'm needing to be cognizant of is that ultimately I'm going to be, as I said, I'm going to be comparing light from different filters with each other. Hold on. Nice. Also, another pro tip. When observing, when data reducing, music is key. You have to have you have to have appropriate music for what you're doing. Because if not, then I don't know if you have a soul or not. Because I just cannot sit in silence and do this. Obviously, since I'm really essentially talking to myself at this point. But music, it must have. Anyway, one of the things to be cognizant of is I'm going to be comparing light from the V filter, for example, from the B filter and from the R filter. But in order for it to make sense, I really have to be comparing apples to apples here. I have to be comparing data that was taken, obviously not simultaneously, but contemporaneously. So the way the data was taken was that an image was taken in U, then an image was taken in B, then an image was taken in V, then R, then I, and then repeated. And so what I'm going to do is in each of those cycles, I'm going to be comparing the B image to the R image. So I want to make sure that I have the same number of images in each of the filters so that I don't somehow get mixed up and start comparing image data from one filter cycle to the next, because as I've already demonstrated, this thing changes brightness pretty quickly. So it wouldn't be appropriate to compare the brightness of the star system at an early time to any really late time, because the two just aren't the same situation. The star is literally moved and is presenting a different face to the observer, and so it's not appropriate to compare those two. So you want to compare images that are as closest to each other in time as you possibly can. If I could have taken all of this data simultaneously, I would have done that. But fortunately, that's not how the telescope was built. So yeah. So that's what I'm doing here. Is in the spreadsheet I have listed what are the so these are in the eye, Um, Image 1027, 28, 29, so forth and so on, are in block 1. So I'm going to take and roughly I'm going to just put 10 images in each. That's the goal. And then I'm going to go back and see whether or not they all kind of compare. They match up. And yes, you all have to deal with my music. Or you can mute, either one. I also have the memory of a goldfish, which is why I will probably be checking and rechecking where I put things. 7, 8, 9, 10, 11, 12. Okay. So now. Shoot knockers. That's not what I wanted to do at all. This is why I love having 2 giant freaking screens. Anyway, what was I doing? Yeah. Oh, before I forget, what I need to do is I need, just in case, I need to save this data. Mag. All right. Just in case something wonky goes and I lose it. Would help if I actually put in the right numbers. Okay, so here, this is an example of what I was talking about in terms of apples to apples, uh, whether or not to compare the appropriate frames to each other. So, for example, if we look at block 4, if we look at the numbering of the image so images in different filters with the same number were taken during the same cycle. So essentially, the 1057th cycling of U, B, V, R, and I, that's what those images were taken in. So I can compare the 1057 R frame to the 1057 I frame, and that would still be scientifically legitimate because the amount of time it takes to go from R to I, the star hasn't appreciably changed very much. But if I were to come over here, and if I were to go to block 8, and I were just to naively continue to compare these things, if I wanted to compare 1101, I would not want to compare the R frame 1101 to the I frame 1097 because a significant amount of time has elapsed between those two frames, and the star has physically changed in that, or at least the physical orientation of the star has physically changed with respect to me. And so, therefore, it's no longer comparing apples to apples. It's no longer scientifically justified to do so. So, I'm already going to have to figure out a way of getting these back into alignment if I want to be able to compare them. So. Needed someone I can trust. I don't care. Dead sea. Say to me, it seems. That looks like it's going to be problematic. Wait. Heidi! Yes, that is in fact Creaky Blinder as my notification. Cell phone notification. Thank you, Creaky. Letting me know that somebody on my role-playing Discord just decided to say something. Anyway. The Dead Sea. Dead Sea. All right. Let us do this. Nope. All right. I'm glad I saved that because now I'm going to clear those measurements, and I'm going to start in on the R band. So I need to rename my folders. That works. All right. So. All right. So what I'm going to do here is, so when you have a scientific image, when you have a scientific CCD image, there are three essential errors that you need to account for in the in the pixels. So a CCD image, pretty much just much like any other digital image, is composed of pixels. There are discrete locations via which there are discrete locations that are photosensitive. So light will hit those pixels, and then a certain amount of electric charge will register, and that's what the computer interprets as counts or brightness. The larger the amount of charge in a particular pixel, the brighter it's going to appear on the screen. So, for example, the pixels comprising this star had a lot of light hit them, or comparatively speaking, a lot more light hitting them, and so it looks much brighter. It's weird. Oh, never mind. That's a period, not a comma. And so that's why it appears white, is because there's more electric charge on those pixels. Now, CCDs, obviously, because they are made by man, are not perfect. There are three things that need to be taken into account. That is the pedestal on the pixel, the dark current which is running through the pixel, and the sensitivity, the inherent sensitivity of that pixel. Because quantum mechanics is a thing, not every pixel is going to be born equal. Each individual pixel is going to have what we call a quantum efficiency, meaning that one pixel is going to be just slightly more or may just be slightly more sensitive to light than the adjoining pixel next to it. And that's going to be randomly determined basically due to quantum fluctuations within the material. So one pixel, 85 out of 100 photons may be registered in that pixel every time it is exposed to the light. The next pixel over, maybe it's 86 or 85 and a half. The point is that each individual pixel is not going to relate in the same, is not going to be as sensitive to everybody else, not a even quantum efficiency over the entirety of the chip. Because of that, and because sometimes some of the pixels will just crap out mechanically and just go dead, the manufacturers want to avoid any sort of any sort of scenario where there is a negative pixel, basically where there might be where the computer might interpret negative signal. And so what that does is what they do to derail that inevitability is put in a pedestal or a bias. They basically just say, we're going to say that the zero level of the pixel is actually as if it had 1,600 counts in it, or 1,600 photons that smacked into that particular pixel. So we're going to add 1,600 to the pixel values of every single pixel in the chip. Every time it's read out, it's going to read out how much charge is actually there. It's then going to add 1,600 to that to make sure that there are no negative values. That's called a bias. And so you would take bias frames, which again, I'll explain what those are more specifically in a later time, but you would take a bias frame and you would just basically subtract out that bias. That's what we have here by bias subtraction. I have certain bias images that I've taken along with this data, and I'm going to essentially combine them, median combine them into one master image, and then I'm going to subtract that off of every science frame that I analyze. Dark frames or flat frames rather, basically also address that variability, that quantum efficiency variability, because what that's going to do is that it's going to provide an artificial sort of gradient across the image that is only there because of the sensitivity of the instrument, not because of any astrophysical reason. Additionally, what flats are useful for is if you have any dust in the images. And because this was such a new instrument, really don't have a very good example of that to show you. But what you basically can see, if there are dust particles in the optical system, they're going to appear out of focus. And so it's going to appear as if an octopus just loves you and just starts just sucker kissing all over your image. You're going to have these little dark donuts all over the place. And so you can get rid of those using flat fielding. And what a flat field does is you basically take an image of an evenly illuminated surface, and that gives you a blueprint of the sensitivity of the chip with regards to not only that CCD, but also that optical system, meaning that the dark sucker marks caused by the dust grains are going to be present in that image, and they're going to be present in the exact same way in the science image, and you can literally divide them out or normalize them. And you basically can get rid of any sort of sensitivity that your camera has due to brightness fluctuations based on quantum efficiency differences, or because of dust in the optical train. And then finally, dark current. Because the camera is not at absolute zero, it radiates a certain amount of heat. And that heat can actually extend into the visible part of the spectrum. We kind of see that analogous to the way, if you look at a hot road, the way that the air sort of shimmers, that's in a way basically heat radiation that we can sort of visualize in the visible. Same kind of idea here is that some of that energy that is being radiated as heat from the camera actually is in the visible part of the spectrum. And the camera is dumb. It doesn't know if the photon that hit it, if it's coming from an astrophysical source, or if the photon that hit it came from the camera itself. But thankfully, that we can that energy, we know the temperature of the camera. We know that given a certain amount of temperature, it's going to generate a certain number of photons every second. So if we know how long our science images are, we can take into account the added dark current that has been added to that image based on exposure, say, of 100 seconds. And so that's what the dark subtraction is about. Dark subtraction is I take images that are not exposed to light, and I can use those to estimate the amount of dark current that is in my science images and just subtract that out. This whole thing is what we call calibrating our science frames. Taking those three things into account, we can sub out we can correct for those things in the science frame, and we can actually take data that we are confident in, that is data from astrophysical conditions, not from any systematics within the instruments themselves. And so I am going to click a few clickies. Technical stuff, I know. Oh. Let's bring up the log so I know what it's doing. Right now it is going through the calibration sequence. I am going to now lay down apertures. I know, it sounds sexy, but really it's not. The aperture is the device that I'm going to use to estimate the amount of brightness the amount of brightness associated with the star as it appears on the chip. And so what I'm going to do is I'm just going to place my aperture. This is, zoom out a little bit. This is my target. So I'm just going to click on this. And so what you see here is this bullseye pattern where you have this sort of central disk. That is what the computer is going to do is it's going to add up all of the brightness inside that central disk, and that's going to correspond to the source from the star. It's then going to skip the region of space that is in this first ring, and then it is going to compute the amount of light which is contained within this outer ring, and that is background sky. So inside this inner disk, you have photons from, again, the astrophysical star, the astrophysical object, the star itself, and you also have photons that are being contributed by the fact that the sky is just bright. It has a certain amount of brightness to it because of just ambient light pollution. We want to get rid of that. Again, we are only interested in the light from the astrophysical source, so we need to get rid of that. The way that we get rid of the sky brightness is by sampling the sky around our target that is devoid of any other astrophysical object. So we're only looking at the brightness from the sky. We take an average of that, and then we subtract off. We take the amount of light that we get from the inner disk, and we subtract off the light that we get from this outer annulus, or this outer ring. And that will tell us essentially how bright this star is, or how bright the star appears in this image. But again, this is differential photometry. So that's the target. Now we need to look at our comparisons. And so you can see, hopefully, can I zoom in? Yeah, I'll zoom in. If I set this up right, I have made these rings appropriate sizes so that this star, this little dude here, that little dude is, or dudette, or non-binary individual, is in my gap. And so therefore the light from that star is not going to contribute to either the source inside the disk or the sky background inside that, or in the outer annulus or outer ring. That's mostly true. Not entirely, but it's mostly true. Unfortunately, there's not much I can do with it. But again, also I have also made the outer ring not so thick as to encompass this background star here. And so when you are choosing your apertures, you want to look at all of the stars that you are planning on taking data with, and you want to configure your aperture size, basically the disk size in the center, such that you get all of the star's light. You want this disk, the diameter of this inner disk, to be sufficiently large to capture all of the star's light. You want to set that gap to be sufficiently large so that the background will only sample background stars, or excuse me, background sky, and no background stars at all. And again, you want it to uh, make that width of that background annulus or background ring thin or thick enough so that you have enough signal from the sky to work with again, without getting any sort of background contamination from stars. So, without any further ado, I'm going to place that there. I'm going to place that there. Place that there. And I'll go to that one. And then I'll just click return. And it's going to go through each of the images. Voila! And, oh, hold on. Hopefully. That's not what I want. Here we go. Range. Range. Okay. Apparently it's not plotting very well. Oh, it is. It's just for some reason this thing got really huge. So yeah, whole bunch of but that's only 10 data points. So we'll see what we see when we get further on. So I am going to mark this as provisionally good. Like that. And I'm just going to keep going until something happens, and go from there. Now, you might be wondering why I don't click on every single star in that image. And the reason for it is basically quality of data. The fainter the star is, the less the quality of the data that I'll get from it. So, for example, that fifth comparison, I may not ultimately use it, depending on the quality data that I get, depending on the error bars that are associated with that star. I may just eliminate it entirely because it is kind of at the faint end. It's only a few hundred counts above background. So the signal to noise is not great. The signal relative to the background noise is not fantastic for this particular object. Also, I want to avoid any stars that are on the edge of the image because the tracking for this telescope was not great. And so I don't want the analysis to be stalled because any of the stars have left the field of view, have basically just left the building. So that's why I've chosen these. Obviously, the target I've chosen because it's the target, but I've chosen these four because they are sufficiently bright and they are not. There's no real danger of them actually leaving the field of view. That I do remember from even from 20 years ago. So. Actually, I'm going to put you up. Nope. I'm going to put that up there. All right, that's done. So that's provisionally. Okay. Yeah, you can kind of see if we look over here. You can kind of see that if the blue again is HL Riga, is the binary star. You can see that the star apparently is dimming again. So it's while this stuff appears to be pretty level, not really varying up or down in any consistent way. HL Riga definitely appears to be moving from a bright state to a faint state, which is good times, man. Hollywood, not forgot this, but you did it so good. Make the switch, back to black. So bright and pink. Saturday night, kind of pink. You can see as we populate as we get more data and populate that graph, you can see that um, the change in brightness becomes even more apparent. So, oops. Mhm. I anticipate this failing soon. I know that the telescope was shifted at some point, which is going to throw AIJ off its game. All right. So far, so good. You can see here with this night that decrease, that shoulder going from a high state to a low state is not nearly as wonky as it was in the previous night. And so again, what that tells me is that there was probably some weather, maybe there were some clouds, there was something going on with those images. There was some error involved in those images that was throwing things off, or maybe there is variability in the bright star that isn't regular or is on a very long period, but it's obviously not being seen here. So, yet another reason why you take multiple sets of data on a system over, like, say, at least 3 rotation cycles, because again, it not only will it, well, you take it over 3 rotation cycles because you want to be able to have confidence in what you are seeing is real, as opposed to errors that are being inserted due to observational conditions, technical difficulties, so forth and so on. So, more data, more good. All right. 6 is provisionally good. 5 is good. 6 is good. Okay. And that's where it fails. And you can see the star system, or the, as I like to call it, the TV antenna constellation. TV antenna constellation shifted. I apparently decided that the stars were getting too close to the edge of the field, and so I readjusted the telescope, and now AIJ isn't able to track those stars, and now it's going to just basically fail. So I'm going to have to figure out on which one it failed. I think it's the last one. So nice. So block 7. Cut. Paste. So clearing that. So this brings us to yet another reality of data reduction. You're going to reduce your data multiple times. There's no way to get around it. It sucks. I don't like doing it. It's probably the least fun thing about data reduction, is that you're going to, because of errors in the programs that you use, because of just, the data isn't being read in properly, a myriad of different reasons, you're going to have to redo the same steps over and over and over again, because there are going to be errors in the system. Sucks. It's just a part and parcel of the gig. So it's just something you're going to have to acknowledge and get past. That you're just going to have to so keep your expectations low. So when you're like, all right, I'm going to run this, and great, I can then move on to the next part of the project. No, you can run that and see where it screws up, because it will screw up. And then you're going to fix it. You're going to rerun it, find out where it's screwed up again. And you're going to rinse and repeat that for a while, until finally you can actually move on to you can put that to bed and move on to the next part. Not that it's not to be I don't want that to sound discouraging, but that's ultimately the reality of things. So, all right. if this works. Well, that didn't work. All right, so yeah, like that. That's gonna. Like 7. Okay. Mm, cool. That worked. All right. So we're on to block 8. Oh, and block 7. Block 8. There is a way to actually have AIJ track the stars appropriately, but that involves a something called a plate solve, and I've been beating up my head against that wall. And I said, no, I'll just do it the hard way, this way, or I should say the tedious way. Um, so, like, all right. So if there are any of you out there who are like, why aren't you plate solving, Rob? I'm like, well, for some reason, plate solve continually fails, and I haven't figured out why. So if there's someone out there who is watching this, I doubt it, but if there's someone out there who's watching this who's familiar with AIJ and can point me in the direction of why a plate solve would be continually failing, um, yeah, email me or put it in the comment section. I would be really grateful to know that piece of information. All right, cleared that. Oh, was it this? This is 9. Shit. I did it in the wrong order. All right, here we go. Target comparison. Okay, block 9. It's done. And I am going to this is going to fail. I know this is going to fail. And I'm just going to let it fail. I'm not going to try to second guess it. $27. Bam. 27. Block 10. Block 11. Paste. Hopefully this doesn't fail. Save that. Haha. That worked. Oh, shoot knockers. I think it died at 48. All right. Let's see what. There is no 48. My darling, it is yours. Your mess is mine. Well, shit. That didn't work. Okay, so far so good. That worked. All right, let's see if this works. Doing my own. New clothes and then daddy. bitch next door there. Listen, and I grew up mean. Addiction insane. I'm saying that dream. Out of the same now. Can you jack? Zone number 7. Tennessee whiskey got me drinking in heaven, and that looked good to me. Without a have to pull me to the fiery deep. Thank you, Jack Daniels. Zone number 7. See whiskey got me drinking in heaven, and I got here too long. Okay, that worked. All right. And, wow, that's a piece of. A whole lot of cannot speak. A whole lot of uninteresting. Oh, all right. Halfway through. Okay. Around me. I fall asleep. And back here next to me. Oh, thank you, Jack Daniels. On number 7. Your whiskey got me drinking in heaven, and I'll never once dry. And didn't take up those tears in your eyes. Thank you, Jack Daniels. On number 7. Your whiskey got me drinking in heaven, and it look good to me. I'll have to pull me to the fiery deep. All right, I think that worked. All right, so I think we're good to go with full on R run. Sweet. All right, let's do this. I don't need to build these anymore because they've been built. All right, so just clear the data. Oops. Damn it. Damn it. Anyway. Okay. Okay. There's the data. Fuja. You know what? I'm just going to close this out. All right, let's try this again. The data. I don't know why it's not plotting it appropriately, so I'm just going to restart. Take that down. Why is this way up here? Oh, there we go. All right. I don't know what that was about. All right, sweet. Ooh, that looking pretty. Now, if there happens to be any space deniers out there who are watching this, I'd be real curious as to why this is a thing. Why would the firmament have objects with no? I mean, this isn't a really, really bright thing. This is just, a star somewhere. Why why the firmament would have this going on? Like, why random stars would be doing this? I mean, why not just have all of the stars twinkle the same way, shine the same way? Maybe mix it up, have a couple different colors or brightnesses, but I mean, this is not something you would notice naked eye. I mean, you can, but you'd have to really be looking for it in order to do it. Actually, no, this is not a naked eye object. You actually cannot see this star using your naked eye. So Why are there stars you can't see with your naked eye on a firmament? Don't quite get that. All right. So yeah, if there are people who do not believe in space exists out there who watch this, an answer to that question would be great. And space is full of stuff like this. I mean, it's awesome. At some point soon, I will be entreating the general populace or whoever watches these videos. You know, there's a lot of good science you can do out there. A lot of good astronomy science you can do out there, given modest means. Even a pair of binoculars, you can. There are certain objects that we need data on, like Betelgeuse, for example, that can be done using a pair of binoculars. That is still scientifically relevant. And actually, there are good reasons why we can't actually, as the quote unquote professionals, can't actually get that data anymore. Oops. Actually, I don't want to do that. I'm gonna reset that. Shoot. All right, I think I've gotten 10. I think this is probably my. Yeah, I don't know. Oh, this was the same night, so why would it have been so wonky in R and not in I? Weird. All right. Questions to be answered later when I. Ah! What the? Arrgh. No! You screwed up my data. Oh, I don't know what happened there. All right, let's do this one more time. Once more into the breach, my friends. This is what I'm talking about. You got to do it over and over and over again. You know, the program is kind enough to tell me when it's done, so I should probably, watch for that. See, finished. Put them in the wrong order. Baby. I was going to say, you are still running. I am not going to fall for that again. Okay, this appears to be frozen. Doesn't seem to be exerting a lot of. All right. Three finger salute this. Oh no. Seems to be running. I don't know what it's doing. Let's see if we can reset it and start it again. Hey, all right. If you kick it enough times, maybe it'll actually do it and do what it's supposed to. Finished. This is definitely some of the cleanest data I've seen. So, all right. Oop. Okay. And all right, so one more. Okay, done. All right, well then, let's save these. Save as. All right. R. Oh, I think I see what's going on. The I-band is notorious for being sensitive to water conditions. If there was sensitive to changes in humidity or changes the humidity. If there is a whole lot of cloud, or if there are even a small amount of cloud cover, or a small change in humidity can really throw off observations and eye. Red, not so much. Red's a little bit more stable, but you can see that the ingress, what we call the beginning of the eclipse, and the egress, they're pretty symmetrical, and so really don't expect to see any. There's really no indication of any spots on these portions of the stars. Any spots would be seen up in what the shoulders of this. So um, we'll see, but you can see that the behavior of the check stars is pretty consistent. Um, Again, it's a fluctuation of about 5%, and that's going to translate ultimately. The spread here is going to add another source of error to these observations. So um, we'll see what that does. Um, Spread really isn't 5%. That's actually all of the stars. So the spread is probably more like 1 or 2%. But again, that's getting further on down the line. Um, as it is, I'm going to remove that. All right. Um, all right, howdy. So, I think that is where I'm going to leave it for this evening. I think I should probably get some sleep as I chug some Coke, so I can be back here in about 4 hours. I don't anticipate. I don't know how often I'm going to be doing this. Um, I do want to put out more planned content. I still have that review to give for Taking Back Astronomy. Um, I also want to talk about ways citizen scientists, specifically as astronomy related, can contribute to the field. And I, of course, need to to educate folks on the Big Bang, what it is, what it isn't, what we know, what we don't, so forth and so on. So, um, I think I have one viewer who came in just as my first viewer for the night is just as I'm basically wrapping this whole thing up. Whoever you are, thank you for showing up. But I will be. I am. Morning, Norman. I Yeah, I've been at this for about 2 hours, 12 minutes. I'm gonna go and actually get some sleep or try to get some sleep. But as I was saying, I don't know how often I'm going to be doing these. These basically showing you how the sausage is made from a data reduction standpoint on how to do research. But it's going to be probably fairly because I want to get this project done. I may, in fact, try to do this from basically have this as a sort of journal, as it were, into how the process is taken from taking the data to reducing the data to writing to analyzing the data to writing up the data and actually trying to get it published somewhere. So who knows? But so yeah, on top of the planned content, which I promise I will get out sooner rather than later, I will also be doing this as well. And I also there's so many things that I want to do. I haven't quite got the time yet. But there's a news program that I want to create. But anyway, um, well, so yeah, Kenny Tiger, thank you for being here, and good night. And I will see you all on the flip side. Again, no matter how dark it gets, you are always Stardust.